Hi, I'm Camila.
And I'm Joseph, and here is our design proposal for large-scale production of hydrogen using electrolysis with a green approach. Over the past century, humanity's net carbon dioxide output grew from 0 to 22 trillion kilograms per year. The massive growth of carbon dioxide output is due to the industrialization of society. This influx of CO2 is the main cause of global warming, acid rain, and the hole in the ozone. Our consumption of these fossil fuels far exceed the natural production of these fuels, so eventually they will run out. According to Shafi and Topal, majority of fossil fuels will run out by 2042, and coal will only be available until 2112. At the 2015 UN Climate Change Conference, the Paris Agreement, negotiated between nations, set a goal to limit global warming to well below 2 degrees Celsius and reduce emissions to eventually reach zero emissions globally.
Hydrogen is a very appealing solution to alleviate our reliance on fossil fuels. It is a very versatile renewable energy source. Even the International Space Shuttle uses it as one of its main fuel sources. The direct use of hydrogen does not produce any carbon dioxide. Recently, the hydrogen market has been expanding quite rapidly. The transportation industry has had growing interest in the hydrogen-based vehicles. Toyota, Hyundai, and Honda all now produce fuel electric vehicles. Also, many fuel cell buses are being used in Europe, the US, and in Eastern Asia.
There are many different pathways to produce hydrogen, each requiring input of some form of energy to split molecules to produce hydrogen gas. Currently, the most common method in industry to produce hydrogen is natural gas steam reformation. It accounts for about 97% of worldwide hydrogen production. This is not a sustainable pathway because it produces carbon dioxide. Cleaner alternatives include biological and biomass methods, photoelectrolysis, and high temperature electrolysis, to name a few. Biological methods indirectly input energy to split water into oxygen and hydrogen. Rather, they use energy and other materials available to keep bacteria functioning to produce hydrogen. The main difficulty with this method is the high capital cost to maintain bacteria. Photoelectric chemical cells, or PECs, capture light to decompose water. Although a very green approach, the main challenge for this pathway is the electrodes. Many deteriorate fast and lack stable performance.
Electrolysis is a technique that utilizes a current to decompose water into hydrogen and oxygen. It does this through an anode and a cathode, similar to a fuel cell. At the cathode of an electrolyzer, water uptakes the electrons and forms hydrogen gas and negatively charged oxygen ions. Oxygen diffuses through a solid membrane and reacts at the anode to form oxygen gas. There are many types of electrolyzers, but according to Back et al., oxide materials are best suited to be the electrodes. Although they are not as efficient, they are inexpensive and show great corrosive resistance.
This is the IO diagram of our proposed system, a high-temperature solid oxide electrolyzer cell. Pure water will be fed into the unit, and gaseous hydrogen and oxygen will be its outputs. Gas phase hydrogen was chosen over liquid because hydrogen gas, in a compressed state, has a greater energy density by weight. Very large heavy tanks must be used to withstand these pressures. Also, keeping it in gas phase makes the process less energy intensive since the hydrogen does not need to be cooled to very low temperatures.
Here is a more detailed look into the process of producing hydrogen from water. The stack will be operating at about 800 degrees Celsius and at 300 psi. We input pure water into the system and heat it up using the heat exchangers with our product streams to try to make the system more energy efficient. Our goal is to produce about 50,000 kilograms of hydrogen per day. The stack is made up of planar solid oxide cells similar to that used in the research study done by Cal M. Stutz et al. Production of this size would require approximately 1,840,000 kilowatt hours per day.
In our design, we considered environmental and social impacts along with potential safety hazards. Starting with environmental impacts, if this process is energized by electricity produced by solar or wind power, it would have no greenhouse gas emissions. Assuming complete conversion, the only emission from the system would be oxygen, which will be disposed of in a safe manner. This system requires about 450,000 liters of water per day to reach the desired production rate, and this is assuming complete conversion. This system is definitely not suited for a dry or drought-prone climate such as California.
In addition, if the system is built, it would be a pioneer in the hydrogen production industry. As stated before, 97% of all hydrogen is produced through natural gas reformation. This would help develop the hydrogen infrastructure, which would allow hydrogen-based technology to grow and ultimately lessen dependence on fossil fuels.
This process will be operating at very dangerous pressures and temperatures. All equipment must be properly insulated and strong enough to withstand these conditions. Oxygen is a very flammable gas and has to be handled and released properly. Electrolysis deals with voltage differences between electrodes. If technicians or engineers must be on site, they need to ensure that they have proper equipment to keep them safe.
Using a production rate of 50,000 kilograms of hydrogen per day, a simple material balance was done assuming 100% conversion to determine the rate of water that must be fed. Prices of $2.48 per kilogram of hydrogen and 17 cents per kilogram of pure water were used to calculate profits. It was determined that the net profit per year for this process is $14,783,331. The break-even TCI was determined to be $147,833,317, assuming the return on investment is 10%. Calculations can be found in the attached documents.
In our first alternate design, instead of pure water, our system will have an input of seawater. The waste stream contains whatever particulates were in the seawater upon intake, such as pollutants, salt, and possibly even sand.
Based on Stutz et al. Research, our second alternative has two electrolysis pathways occurring simultaneously. Carbon monoxide and hydrogen are produced together, making what is known as synthetic fuel or syngas.
Design alternative A was ultimately not chosen because the reverse osmosis is an energy-intensive and expensive process. The regular process alone is quite expensive, and adding on another energy-intensive process will make it undesirable. Design alternative B was not chosen because production requires multiple gas inputs and deals with carbon monoxide, a very toxic gas. Further safety precautions will have to be installed. Since the capital cost of this system is already very high, this alternative is less appealing than the original.
According to the economic analysis done on the proposed IO diagram, the process proves to have profitability. However, it is important to do some further economic analysis to take into account the utilities and other capital costs, such as the electrolyzer unit, heaters, storage tanks, compressors, etc., that are required to accurately determine the profitability of this process. In addition, further research into making this process more energy efficient will be a priority to reduce costs and overcome these limitations for hydrogen production via electrolysis.